Okay, couple of warm-up questions. So here they are. What are the sine and cosine of negative an angle? So that's the first one. Second one, same thing, but for pi root 2 plus the angle, and same thing, but pi root 2 minus the angle. So what are sine and cosine? What can you say? So like you have some angle, theta, and what can you say about these things? So take a minute and see if you can write some stuff down. Okay, talk with a neighbor for a little bit, please. Are you going camping?
Oh, I'm returning some stuff.
I see.
Sorry.
Okay. Okay. Let's look at the first one. If we have the angle negative theta, right? You've got theta. You've got negative theta. What can you say about the sines? Sine of negative theta. What's the relation between sine of negative theta and sine of theta? I forgot my random number generator. Right. So the sine is the y coordinate, right? The sine is the y coordinate, right? You can see from the picture by using, say, similar triangles that that the sine of this guy is the negative of the sine of the other guy, right? So this is going to be negative sine theta. And what about the cosine? Anybody? It's going to be the same, right? Cosine of negative theta equals cosine of theta, right? Okay. Now, what about? Actually, I think I'm feeling that this one is easier. If we have an angle theta, and then we look at pi root 2 minus theta. So here's pi root 2 here, and we subtract off theta. So that's this thing here, pi root 2 minus theta, right? I think you can probably see what's going to happen here, right? The cosine of theta, the cosine of pi root 2 minus theta is going to be, can somebody just say it out? Isa, how about you? Cosine of pi root 2 minus theta, can you see from the picture? Maybe the camera is blocking you. Don't know? That's okay. So let's think. Cosine is the x-coordinate, right? Is the x-coordinate. So you want, here is cosine. This dot has coordinates cosine theta, sine theta, right? Right. And what you want to see about this other dot is that it's a reflection, right? It's a reflection across the y equals x-axis, y equals x line, right? And so you see that the cosine, the x-coordinate of this is the y-coordinate of this. The y-coordinate of this is the x-coordinate of this, right? There's a reflection across this line. So you see that this is going to be the sine, and this one is going to be the other one, the y-coordinate of one of the points is going to be the x-coordinate of the other point, right? Everybody see that? Okay. Hopefully this should be intuitive. Hopefully you're like, oh wow, this is great, right? You look at it, say, oh, there are all these identities that we have to remember, but we actually don't have to remember them, right? If we understand what's going on, it's like, oh, okay, just draw a picture and use a little bit of reasoning. Say, oh, look, if we're looking for the cosine of this minus that, well, that's just a reflection here. So the cosine and sine get switched, right? Okay. So I hope that you all feel that that's natural, that that's something that you could do. Okay. When you're doing mathematics, you always want to think, can I do it? Can I do it myself? Right? How could I do this myself? Would I be able to do this myself? How can I make it so that this is natural to me, right? Why is this obvious? Why is this obvious? Okay, because at some point it was obvious to somebody, right? And you guys are all human beings, so maybe we can hope that we can see things that other people do. That might not always be true, but you do your best. Okay, the last one, pi over 2 plus the angle, right? So this is one we actually drew before. Pi over 2 plus the angle. So here's pi over 2 again, and we add on the angle here. Right? We add on the angle here, and we see that I don't know. How do you want to think about this? Right? This is, you've got some coordinates here. Right? These are cosine theta, sine theta, and you've got cosine pi over 2 plus theta, sine pi over 2 plus theta here, right? Can anyone see what these coordinates must be? Like, what's the relation between these coordinates and these coordinates? Let me give a hint. How about we take the reflection here, right? These coordinates, what are these coordinates? If these are x and y, what are these coordinates? Y, x, right? Y, x. And what are these coordinates? Negative y, x. Right? Negative y, x. Right? Because it's the reflection across the y-axis, right? And so you see that this thing is going to be negative y, so this is going to be negative sine theta, and x is cosine theta. Right? So we've got our identity. Now cosine pi over 2 plus theta equals negative sine theta. Sine of pi over 2 plus theta equals cosine theta. Okay, I'm going to write all those things up in the corner here because we may have to refer back to them at some point. So sine of negative theta is negative sine theta. Cosine of negative theta is cosine theta. Cosine of pi over 2 minus theta is sine theta. Cosine of pi over 2 minus theta is cosine theta. Right? And cosine of pi over 2 minus theta, pi over 2 plus theta is negative sine theta. And sine of pi over 2 minus plus theta is just cosine theta. Okay. Okay. So So that was just the warm-up, basically, but it'll be useful to us. So let me ask you a question. If you have a function, f is a function is it true that f of x plus y equals f of x plus f of y? Is that true? Is that always true? Whenever you have a function, f of x plus y equals f of x plus f of y? No. No. Can you think of a function for which it's not true? Any old friendly function that you've met before? So like if I take square, suppose I have the squaring function. Is it true that x plus y squared equals x squared plus y squared? No, right? That's so not true for the squaring function, right? Although people sort of secretly, I think people hope that this is true. So you often see students say, "Oh, this is true, right? You can just pass the square inside." But no, that's not true, right? So yeah, so that's not true. Any other functions do you know that for which this is not true? Anybody throw out something? More complicated or simple? Is it true that, say, like log of x plus y equals log x plus log y? Is that true? No, it's not true, right? We had something like log of x times y equals log of x plus log of y, but not log of x plus y, right? So log of x plus y, no, that's not true. Okay, so what we're going to do today are find what are called addition formula. So this is section 8.1, addition formula. Addition formulae, I guess, for this trigonometric functions, so for sine and cosine. So here they are. There are formulas. Sine and cosine are nice because they actually have formulas for sums. If you have sine of alpha plus beta, or you have cosine of alpha plus beta, they're actually very neat formulas that give you the answer to this. Okay, so let me put up the first one. Sine of alpha plus beta turns out to be sine alpha cosine beta plus sine beta cosine alpha. Sine alpha cosine beta plus sine beta cosine alpha. Okay, so for example, right, if we were looking at sine of pi over 2 plus theta, this formula would say, that we're going to get sine of pi over 2 times cosine theta plus sine of theta cosine pi over 2. Okay, right, so just substituting in, this is my alpha, this is my beta. What's sine of pi over 2? That's the y-coordinate of this point on the unit circle. So that's 1, right? Okay, so this is a 1. What's the cosine of pi over 2? It's 0, right? Cosine of pi over 2 is 0. And so we see that this term vanishes, right? And what we're left, this is 1, so we're left with cosine theta. Right? And that's what we saw geometrically. Okay, but now we've got this algebraic formula that gives it to us. So we have sort of there's like a super version of these facts that we got before. Right, we were able to show something like this, but actually we can get this formula that works for any alpha and any beta, right? Just plug in alphas and betas, whatever you feel like, and get out some expression for it. Okay. Okay. There's also a formula for the cosine. Cosine of alpha plus beta turns out to be cosine alpha cosine beta minus sine alpha sine beta. Okay. And if we worked out, cosine of pi over 2 plus theta, we would end up saying that it's negative sine theta. But I'm not going to do that. So there are these nice addition formulas for the sine and cosine. Okay. So, this is great. It's a generalization of these things that we were looking at before. Right? So we've got these pretty nice and kind of pretty formulas that come out of this. Right? It's much nicer than trying to do something for the square root function, say, or this. Right. And basically, what they allow us to do is to extend our knowledge, right? So, like, we know things like sine of pi over 3. We know things like cosine of pi over. We know things like cosine pi over 6. But now we can get like the sine of pi over 3 plus pi over 6, right? Or or whatever, right? We can move on. We can get to combinations. We can move on to combinations of our simple angles, right? So our simple angles we were able to get geometrically, right? And now we've got this formula that extends us to all sorts of combinations of those angles. So this is pretty nice. Okay. Any questions so far? I guess all I've said is we've got formulas. Okay, so nobody will argue with that. Okay, so one comment is that this formula for the sum, we also get, that automatically gives us a formula for the difference, right? Because we can think of this as the sine of alpha plus negative beta, right? And then we just plug in here, right? So we would get sine alpha cosine negative beta plus sine negative beta cosine alpha, right? So, this is nothing remarkable. A plus B is the same thing. Sorry, A minus B is A plus minus B, right? That's something you've known since you're little, right? Okay, and then, right, you say, okay, we know that cosine of minus theta is just theta, right? So this is going to be sine alpha cosine theta, right? Sine of negative beta is minus sine beta, right? And so that gives us this formula, right? Sine alpha cosine beta minus sine beta cosine alpha, right? So the difference gives you this formula, but don't remember this. Just plug in minus beta and remember this, or figure out this, understand this. Don't waste your brain space, right? With stuff that you can understand. Right? Yeah, basically, when you're trying to learn stuff, you want to figure out like what's the minimal amount of memorization I need to do, right? Like I only want to remember certain things, and everything else I want to be able to reconstruct, right? As long as it's not too complicated, right? And so like it's much easier to well, it takes more effort, but once you understood this, then you don't have to remember so much. Okay, so similarly, we could get a formula for cosine alpha minus beta, right? And that's going to be cosine alpha cosine beta, right? And so you see what's going to happen, right? The minus beta isn't going to change the cosine, right? When we put in the minus beta here, that's the cosine of minus beta and cosine beta are the same, right? When we put in the minus beta here, we're going to get a negative sign, right? Because not sine of negative beta is going to give us negative sine beta, so we get this, right? We get cosine alpha cosine beta plus sine alpha sine beta. Okay, but hopefully you're like, okay, why? Let's get on with it. This is right. just all we're using is this pair of facts here. Everybody, are you guys okay? Yes? No? If you're not okay, don't be embarrassed. Just raise your hand. I've been going to the French table at Oldenburg recently. My French is so horrible. But it's sort of like the same thing. You want to just, say what you can and then get feedback and then, get better. So shamelessness, I think I told you, is the key. I did French for five years in junior high and high school. And I really loved it at the time, but it's been 35 years since then. So, yeah. If you want to see your professor embarrassing himself, come to Oldenburg, join the French table. Okay. Okay. So for example, let's do some examples. Here's an example. Sine of pi over 4 plus pi over 6. Okay. So this is something that not so obvious, right? But we've got this formula now. We know it's going to be sine pi over 4 cosine pi over 6 plus sine pi over 6 cosine pi over 4. Right? Right. Do you guys remember these? What's sine? Anybody remember sine of pi over 4? Root 2 over 2. Same for the cosine, right? Cosine pi over 4 is also root 2 over 2. And then cosine pi over 6, remember, this is the half guy. The sine is a half, right? Sine is a half, and the cosine was root 3 over 2. So you get the square root of 6 over 4 plus the square root of 6 plus the square root of 2 quantity of 4. Okay. So, right, you see what I mean about extending our knowledge, right? We knew the sine and cosine for some rudimentary angles, and now we can just combine them however we feel like and get other sines and cosines of other angles. I've been ignoring the tangent, right? Hopefully you all have read in the book that the tangent is just the sine or the cosine. So, to me, the main thing is to understand, the sine and the cosine. Okay, well, we just quickly think about it. Cosine theta, this is negative sine theta, this is just cosine. Okay. Okay, so one thing that is will be really important in the next course will be the fact that these addition formulas allow you to calculate rates of change. Okay, so let's remember, average rate of change. Average rate of change, let's look at, say, the average rate of change of the cosine over some interval x plus h. Okay. can somebody tell me, so my function is the cosine function, say, and I want to look at the average rate of change, the average rate of change. Maybe I should use x, since we often use x for functions. Can somebody remind me what what we mean by the average rate of change? It's going to be the change in f or the change in x, right? So what should I write over here? Vivi, how about you? Do you mind telling me? Average rate of change, do you remember? If you don't, that's okay.
I don't know what
Change in f, so it's, remember, so you think you've got 2 points, x and x plus h. You've got your function, right? And these are this is the line y equals f of x, right? Well, the change in x is going to be the difference in x values, right? The change in y, the change in f is the change in that f goes through. So it's the difference between these values. Okay. So right here is this height is f of x plus h. This height is f of x, right? So change in f is just going to be one of them minus the other one.
So just h.
This is going to be h, right? Because x plus h minus x is h, right? This length here is h, right? But this height here is going to be f of x plus h minus f of x. Okay. So in case you've forgotten, so you get f of x plus h minus f of x over h. But our f is the cosine function, right? Our f is the cosine function, and so we are going to get cosine, so that is, let me bring it over here, that is cosine of x plus h minus cosine of x over h, right? Okay. And we've got the formula, we have this formula for cosine of a sum, right? And it says, I've already forgotten, that the cosine of a sum is the product of the cosines minus the product of the sines. Oh, and then it gets subtract off. Sorry. Forgot something. Okay, so I'm going to sort of regroup things. This part isn't very relevant to what we're doing now, but it will be important next year or next semester. I'm going to group things involving cosine x and involving sine of x. So I'm just rewriting this. I broke this thing into 2 parts, and then just factored out cosine x. Okay, so this is the formula for the average rate of change of the cosine if we have our cosine function, remember our cosine function looks like this, and if this is x plus h, then that gives me the slope of this, secant line here, right? The average rate of change, recall, is the slope of the secant line. Okay, and what you're going to do next year, next semester, is you're going to let the interval become infinitely small, so that you can get the slope of the so-called tangent line, the slope of the tangent line here, which corresponds to the instantaneous velocity of this function. Okay, and what happens when you do that? So you don't have to know this, but just to give you some foreshadowing, when you let the size of the interval shrink down to 0, what happens is that this whole thing turns to 0, and this thing turns into 1. Okay, this thing turns to 0, and this thing turns to 0, this thing turns to 1, and you end up with sine x, actually. So the instantaneous rate of change turns out to be the sine function, right? The instantaneous rate of change of the cosine function turns out to be the sine function. And something similar happens for the sine function. Yes, please. -1. Oh yeah, so this whole term here comes from this guy and this guy, right? So I've sort of grouped all this stuff here, and then this thing becomes this thing over here. Okay, so I've grouped these guys together, and then I factored out cosine x. Factoring out cosine x gives me cosine h minus 1, right? Because I factor out the cosine x out of this thing and out of this thing, right? So I'm distributing the cosine x factor out, right? If I put it back in, so like using by the distributive property, I can put it back in, right? Basically, if you don't, yeah, right? You can put it back in. This would be cosine x times this minus cosine x times -1, minus cosine x times 1, right? That would give me these terms back. Okay. Okay. So this last part you don't really have to worry about yet. But this is just to show you what's really useful about these addition formulas. Why people care about these addition formulas, because they tell you about actually you can get information about the average rate of change and then the instantaneous rate of change, and that leads to the world of physics, right? When you start talking about instantaneous rate of change, this is what Newton did in the 17th century that led to the revolution in physics. Yes, please. This one? This one?
No, between the cosine of h and the sine of x.
This one? Oh yeah, that's a good question. What happened? That should be a minus sign, I think. Sorry. Yeah, sorry. Sorry. This should be minus. Sorry. Thank you. Thanks a lot. Yeah, that's embarrassing. Yeah. The derivative of cosine of x is negative. I'm sorry. The slope is going to be negative sine x, not sine x. Okay. Okay. Okay, let me think. What should we do here? Okay, so yeah, let's do that. Okay. So another thing that comes out of this is what are called double angle formulas. So, right, right. this is just going to be the sine of theta plus theta, right? And so we can use our addition formula on it, right? And we get, you know, sine of theta, right? So this is going to be sine of theta plus theta. And then we use our formula. Remember our formula, sine of the sum is going to be sine alpha cosine beta plus sine beta cosine alpha. Right? So we just apply that with alpha and beta being equal to each other, both being theta, and we're going to get sine theta cosine theta, sine beta cosine theta plus sine theta cosine theta. Right? So we end up with 2 sine theta cosine theta. Okay. So anyway, so the point is that these formulas are are pretty handy. Okay, so right now we're just looking at, like, we're just taking these formulas as being true, and then we are applying them. Okay, but you should always say, like, why should we believe these things to be true, right? So why do we believe this? Why do we believe these formulas? Okay, and let me give you an example of one argument. Okay, so why is it true that, so let's look at one example, which is cosine of alpha minus beta equals cosine alpha cosine beta plus sine alpha sine beta. Why is this? Why does this happen? Okay, and in my notes I have that this argument is due to the great mathematician Cauchy from the 18th century, French mathematician from the 18th century, who was famous for getting results in a field of math called complex analysis. Okay, so that's like doing calculus, but with complex numbers. The theory of calculus with complex numbers, which turns out to be like so much better than calculus with real numbers, that there are professors who fight with each other over who gets to teach the class. That's how good that course is. Okay, including myself. Okay. Okay, so the argument I'm going to show you is due to the great mathematician Cauchy. And here it is. Okay, so we want the cosine of right? We want cosine of alpha minus beta, right? So let's suppose that this is it. Okay, let's suppose that this angle is alpha minus beta. Okay, and we're on the unit circle as usual. And we make this triangle here. Okay, so this point is, of course, 1, 0, right? Okay, and this point is, of course, cosine alpha minus beta sine alpha minus beta. Right? Just by definition, of course. Okay, so now what we're going to do is we're going to rotate it by beta. Okay, we're going to rotate this whole thing by beta. So suppose that beta, it looks like this. Okay, then we take this guy, we rotate it by beta, right? And we get something like this. So this is alpha minus beta. This is beta. Right? Okay, so I've just taken the whole triangle over here, and I rotate it by beta, right? Then what's this point here? This angle is beta, so what are the coordinates of this point? Somebody just shout it out for me. Anybody? unit circle again. This angle is beta, so the x-coordinate is cosine, thank you. Right. Cosine beta, the y-coordinate is sine beta. Right. What's this angle now? What's this combined angle here? Brisa? This angle is beta, this angle is alpha minus beta. So together it's going to be, if you add them together, alpha, thank you. This thing is going to be alpha. Was that too easy? I think that was too easy. People didn't want to say it. Okay, so you get cosine, so the coordinates at this point are cosine alpha, sine alpha. Right? Okay. Any questions up until this point? Okay. Let me come back over here. So Cauchy's cool idea is to say, well, look, you know, these distances are the same, right? The distance from here to here is the same thing as the distance from here to here, right? And that will give us a relationship between the cosine and sine of the cosine of alpha minus beta, and you know, cosine alpha, cosine sine alpha, and cosine sine beta. Okay, so that's the cool thing, right? This thing says, well, look, you know, these things are actually kind of clearly related to each other, right? So let's look at the distance formula, right? Cosine alpha minus beta minus 1 quantity squared plus sine alpha minus beta minus 0 quantity squared. Everything square rooted is going to be the distance over there, which is cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared. Everything square rooted. Okay. So we just say distances, the distance doesn't change. Right? When we take this triangle and we rotate it over, we haven't deformed the triangle, right? It's the same triangle. So this long leg of the triangle is the same length. Right? So the square root of you know, x1 minus x2 squared plus y1 minus y2 squared equals the same thing over there. Okay. So I'm going to erase the square roots because I'm just going to square both sides. Right? Right? The squares of the distances are going to be equal. The distances are equal. The squares of the distances are going to be equal. Right? Okay. So what do we see? Right. Okay, so let's work that out. What do we get when we square? So the left-hand side is going to be cosine squared alpha minus beta minus 2 cosine alpha minus beta plus 1. Right? So I'm just squaring this term. Right? And plus the square of this guy. Oops. The square of that guy is just sine squared alpha minus beta. Okay. And then on the right-hand side, I'm going to get the square of this term. So I get cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. And then I square this term, I get plus sine squared alpha minus 2 sine alpha sine beta plus sine squared beta. So I haven't done anything other than use the fact that a plus b squared is a squared plus 2ab plus b squared. Okay, that's basically all I'm doing. I'm just squaring things. Okay. I squared this thing, I squared this thing, I squared this thing, I squared this thing. I guess I'm using the minus version. Anyway. Okay, so we've got a couple minutes left. What happens? What happens on the left-hand side? Let's look at this left-hand side here. Cosine squared a minus alpha minus beta minus this plus 1 plus sine squared alpha minus beta. What can we do? We can simplify that. Anybody see it? Anything that we've got a cosine squared and we've got a sine squared. Well, what's cosine squared plus sine squared? 1, right? We get 1. So these two guys turn into 1, right? So right. So we get 1. So on the left-hand side, we're going to get -2 cosine alpha minus beta plus 2. Right? We had a plus 1. We got another plus 1. That gives us plus 2. Right? What about on the right-hand side? Well, we've got a cosine squared alpha. We've got a sine squared alpha. That gives us 1. We've got a cosine squared beta and a sine squared beta. That gives us another 1. Right? Is it right? Yes? Right? Okay, so we've got 2. On the right-hand side, we've got a 2 from those underlined things. And then we've got a -2 cosine alpha cosine beta -2 sine alpha sine beta. Right? So that is from the statement that the distance hasn't changed. Those distances are equal, right? Well, we can cancel off the 2's, right? We have a +2 here, we have a +2 here. We subtract 2 from both sides, right? And we get -2 cosine alpha minus beta equals -2. I'm going to factor out, I'm going to distribute out the -2 here. I get cosine alpha cosine beta plus sine alpha sine beta. Right? Right? So I've got these two terms. They both have a -2 on them, so I pull the -2 out, I distribute the -2 out, and I get cosine alpha cosine beta plus sine alpha sine beta. Right? If you feel uncomfortable, just distribute it back in and you see that you get the thing up here. Okay. It's funny, but we use the distributed property a lot, so you do need to know you do need to remember the distributed property. Okay. And then you see what's going to happen. We're going to divide both sides by -2, right? So we've got a -2 on both sides. Divide both sides by -2, and lo and behold, we get their formula. Okay, right? So that's why this formula really is true. I had a professor in college who would arrive in the classroom. The board wouldn't be erased, and he would be like, and just start erasing randomly. And he'd like leave formulas, like pictures here, formulas there, whatever. And then he would, amazingly, he would start his lecture, which had nothing to do with the previous lecture, from this side of the board. And then as he worked his way across the board, he would work in whatever he had left into his lecture. And we would always cheer when he did this successfully. He's like a brilliant guy. Anyway. Okay, see you all next time I suspect, or maybe. I hope.